Hey, welcome back to the channel. We're starting off with an HSC question from the very recent 2021 HSC. We've got four statements and one of them is false. So if you're playing along, pause the video and see if you can figure out which one of these four statements is not always true. So see if you can find a counterexample that disproves one of these four statements. Let me know how you go. All right, if you are staring at your screen and screaming out option D is false, you are smack bang correct. So A is less than B implies that 1 on A is greater than 1 on B. This is true if A and B are either both positive or both negative, but have a look at this counterexample. So minus 2 less than 3, that is true. But if we take the reciprocals of both sides, negative a half greater than positive a third is not true. So there is a counterexample that makes this not always the case. All right, today's lesson, really fun one. It's all about solving polynomials involving complex roots or complex numbers. Let's take a look at some further levels of factorization we can achieve in this course as opposed to the advanced or the extension 1 course. So right here is a polynomial. We can see it's degree 5, and this is as far factorized as you would go in the advanced or extension 1 course, okay? However, if we wanted to be a little bit more sneaky, we could think of this x squared take away 3 as a difference of two squares, where we have x squared and we have root 3 squared. So if we wanted to factorize this over the real numbers, we could split it up as a difference of squares, and now we have 4 distinct factors. Okay, now if we want to get really, really Larry, we can think of this x squared plus 1. If we use our extension 2 tricks, we can say, well, 1 is the same thing as negative I squared. So now x squared plus 1 is a difference of two squares, x squared minus I squared, and we can factorize it like this. So here is our polynomial factorized completely over the complex numbers. Okay, so a degree 5 polynomial may only have 1 or 3 roots in the real number system. However, in the complex field, a degree 5 polynomial will always have 5 roots because you can always keep factorizing as long as you are clever in how you do it. All right, some background info for today that's going to help us achieve a few questions. First of all, we have a polynomial p of z, and it has real coefficients. Okay, so none of the coefficients of our z terms are imaginary. Now, if we sub in a number alpha and we get out an answer of beta, and let's say alpha and beta are complex numbers, we know that if we subbed in the conjugate of alpha, the answer we would get from the output of our polynomial would be the conjugate of beta. Okay, so you sub in a number, you get a number. If you sub in the conjugate, you get the conjugate. Okay, the proof of this is, just trust me, I'm a maths teacher and I wouldn't lie to you. Extending this, we go to what's called the conjugate root theorem, which is basically saying if you know that a complex number alpha is a root of the polynomial, this tells us that the conjugate, which is alpha with a little hat on, this will also be a root of a polynomial. Now, like I said, this is only for polynomials with real coefficients, okay? So as long as it's a regular looking polynomial, your roots will be in conjugate pairs. Okay, so yeah, when we're looking to factorize or we're looking to solve for roots, we can expect to see pairs, which makes things a lot simpler because once you've got one root, you've got 2. All right, let's dive into a bunch of examples. So starting off with a kind of mild one, we have a cubic polynomial, and we are going to express this as a product of complex linear factors. So we are going to fully factorize this as much as humanly possible. Okay, normally for a polynomial, you're trying to find a factor that you can do some long division with. Fortunately for today, we can sort of work around long division, and we can actually factorize this using grouping pairs factorization. So we can take an x squared out of the front 2 terms, and we can take an x out of the back 2. Now we have a common factor of x minus 3, so we can factor that bracketed term out the front, or the back, I guess, and we end up with x squared plus 5 multiplied by x minus 3. Now to factorize x squared plus 5, we'll use a similar trick from before where we write plus 5 as minus 5i squared. Now we have a difference of squares, and we can factorize this as x minus I root 5 and x plus I root 5. So here we have a product of linear, so linear means there's no squared terms, and we have complex factors. So there is our fully factorized cubic polynomial. Lovely. All right, on to the next one. we have a polynomial in terms of z. We've got a cubic polynomial. Part A is show that 2 plus I is a root of the polynomial. Okay, so the way we show that this complex number is a root is the same way we do it in extension 1, where we just need to show that if we sub this number into the polynomial, we get 0 as an answer. Okay, so roots make the polynomial equal to 0. So let's chuck her in. Let's do polynomial of 2 plus I. So I've got to do a cubic, which is going to be a bit of a headache, a squared, and then, yeah, just be very careful with your eyes and make sure you don't have any negatives in the wrong spot, or it's all going to be stuffed up. Okay, expanding 2 plus I cubed. If we want, we can do a little binomial expansion. So we can have 2 cubed, and then we have 2 squared times I, and then multiplied by 3, because it's our 1, 3, 3, 1 row of the Pascal's triangle. Then we have 2 times I squared, and then again multiplied by 3, and then we have I cubed. Now for our squared, we have 2 squared, and then we have 2 times I, and then doubled, and we have I squared. Okay, I'm not going to over explain all this, but as expected, when we tidy everything up, we get 12I, we get minus 6 here. Don't forget that I cubed is the same thing as minus I, because we split this up as I squared times I. You already know this, what am I talking about? Anyway, if you expand it all out properly and tidy it all up, you do get an answer of 0, which is what we wanted to show. We've shown that 2 plus I makes the polynomial equal to 0. All right. Up next for part B, we have find the other 2 roots of the polynomial. Now looking at P of Z and looking at our coefficients, we can see they are all real numbers. This means we can apply the conjugate root theorem and say if 2 plus I is a root, then the conjugate 2 minus I is also a root of the polynomial. All right, now we can be really clever using our sums and products of roots from extension 1. These facts will be very, very useful for today's lesson. So we know when we sum the roots of a cubic polynomial, or any polynomial, we end up with minus b over a. So this means that 2 plus I plus 2 minus I plus the third root is equal to negative 1 over 1. So because of these conjugate pairs, the imaginary terms cancel out, and we end up with 4 plus gamma is equal to 1. So if we take 4 from both sides, we end up with our last root being equal to minus 3. Okay, there we go. There are the other 2 roots of P of Z, 2 minus I and minus 3. Now part C, hence express the polynomial as a product of factors with real coefficients. Okay, now that we know the roots of our polynomial, we can write it in factored form like this. So we have Z minus 2 plus I, Z minus 2 minus I, and then Z minus minus 3. Now, to have our answer as a product of factors with real coefficients, we're going to need to multiply these 2 conjugate terms together. There's a clever way we can do that. If we expand out the interior brackets, we have Z minus 2 minus I and Z minus 2 plus I. And then, of course, Z plus 3 just chilling on the end. Now, if I'm multiplying these 2 brackets together, the quickest way in my mind, if I don't want to do a big FOIL expansion and, carry on, think of this as like a difference of 2 squares. We have Z minus 2 minus I, and we have Z minus 2 plus I. So multiplying these 2 together, we can just do Z minus 2 squared, take away I squared. And in my mind, that's just a bit easier, less likely for me to make a mistake, I would think. So we have Z squared minus 4Z plus 4, and then minus I squared turns into positive 1. So there we get plus 5 on the end, and there we have a product of 2 factors where all of our coefficients are real. So we have satisfied the criteria of the question. Lovely, on to the next one. We have, given that Z plus 2 minus I is a factor of the polynomial, and as we can see, this polynomial has all real coefficients, which is great news. Factorize the polynomial over the set of complex numbers. Okay, so straight away, if we look at our factor, and instead of having it as Z plus something, we like to write our factors as Z minus something, because then that thing we're minusing is one of our roots. So we have Z minus negative 2 plus I. This tells us that minus 2 plus I is a root, and then the conjugate root theorem tells us that minus 2 minus I must also be a root of the polynomial. So straight away, we have 2 out of the 4 roots. We've just got to find the other 2 now. Okay, so once again, there's a few different ways we can do this. Number one is we could have had our 2 factors as Z plus 2 minus I and Z plus 2 plus I. We could have multiplied those 2 together to get a quadratic and then do a long division with this polynomial. Again, today I'm trying to use my sums and products of roots to avoid long division because, to be honest, it's just hard to do on a video. But anyway, so here we have our 4 roots plus together. Now I'm going to sub in one of them being minus 2 plus I and the other being minus 2 minus I. This gets us, we have a minus 4 on the left and a minus 4 on the right, which is convenient. The i's cancel out and gamma plus delta is equal to 0. All right, let's get another equation using the product of roots. So alpha, beta, gamma, delta multiplied together for a quartic polynomial is equal to e over a. So we have our 2 roots from before, and obviously gamma and delta still unknown. E over a is minus 10 over 1, so there we have minus 10. Now, multiplying these 2 terms together, we end up with 4 take away I squared. I squared is minus 1, so we have 5 gamma delta equal to minus 10. This tells us that gamma delta is equal to minus 2. Now we have a couple of quick simultaneous equations we can solve together to try and figure out gamma and delta. So I'm going to put those over here. That was cool. All right, solving this, I'm going to put the gamma on the right-hand side. So delta is equal to minus gamma. I'm going to substitute this into the second equation. So gamma times delta is going to become negative gamma squared. Okay, changing this delta to a minus gamma, and then we get minus gamma squared. All right, this gets us that gamma is equal to, gamma squared is equal to 2. So gamma must be plus or minus root 2. So one of them is positive root 2, and then the other one, which is delta, will be negative root 2. So there we have our 4 roots. So now we can write our polynomial in factored form over the complex numbers. We have z with one of our factors, and then the conjugate, and then we have z minus root 2 and z minus negative root 2. There is our fully factored polynomial. It's so beautiful, isn't it? God, I love maths. All right. Example 4, we have a cubic polynomial with a lot of unknown numbers, but the numbers we don't know are real numbers, which is good because, again, it means we can apply the conjugate root theorem, which is very, very useful for a lot of these questions. Okay, given that a solution of the polynomial equal to 0 is 3 minus 2i, and we also know that the polynomial evaluated at minus 2 is equal to 0. Find the values of b, c, and d. All right, let's dive in. So straight away, we know that because 3 minus 2i is a root, we straight away, thanks to the conjugate root theorem, know that 3 plus 2i is also a root. Now, because minus 2 goes into the polynomial and gets 0, it means that minus 2 is the third root of our polynomial. So sweet, now we know what our 3 roots are. It means we can write our polynomial in factored form, and all we've got to do is just expand this out, and we're going to have our polynomial, and we can figure out what b, c, and d are. So let's do that. Let's expand out our interior brackets again. So we have z minus 3 plus 2i, and then z minus 3 minus 2i. Z plus 2 just chilling on the end. Okay, now using our trick again, we'll expand these 2 brackets as a difference of squares, where one bit is z minus 3, and the other bit is 2i. So we have z minus 3 squared, take away 2i squared. So we'll have z squared, take away 6z plus 9, and then 2i all squared will be minus 4. If we take that away, it's a positive 4. Okay, now the 9 plus 14 makes a 13, and now we just got to expand these 2 brackets again. So we end up with z cubed, take away 6z squared. You can probably read the rest. I don't really need to narrate every single step, but anyway, here is the 2 brackets expanded. Let's now just tie it up a little bit, and we end up with z cubed, take away 4z squared, plus z plus 26. There we have our polynomial. So b is negative 4. We can see c is 1 and d is equal to 26. So there is the question done. On to the next one. How many did I do? I can't remember. Probably a lot. All right, quintic polynomial. Let's get really, really high powers now. All right, we've got a quintic polynomial, and the first part of the question is asking us to show that x plus I is a double root. Okay, hopefully if you're watching this video, you are already somewhat familiar with double roots from extension 1. So we know that a double root is a root of the polynomial that is also a turning point. So if we're ever asked to show that a number is a double root of the function, we need to show that if we sub it into the function, we get 0. We also need to show that if we sub it into the derivative, we also get 0. Okay, so it's showing that it's a root and then also showing it's a turning point. That's the definition of a double root if you're thinking graphically. So starting off, let's get our pieces because we're gonna have to do a lot of subbing in here of high powers. So start off with of 1 plus I squared. That gets us 1 plus 2i plus I squared, which simplifies to just 2i. Now, if we want to find 1 plus I cubed, we can just do 1 plus I times 1 plus I squared, which we just figured out is 2i. So just multiplying the last answer by 1 plus I again gets us 2i plus 2i squared, so we get minus 2 plus 2i. Okay, now for 1 plus I to the 4, easiest way to do that is just take 1 plus I squared and square it again. So very clever. So we end up with 4i squared, so we end up with minus 4. And we'll also need a power of 5, so we'll take our, what are we doing here? We're going to take 1 plus I to the 4, which is just minus 4. Multiply this by 1 plus I, which gets us minus 4 minus 4i. Okay, hopefully that wasn't too quick. Now, these are the 4 bits we can chuck into our polynomial. So we'll evaluate the polynomial at 1 plus I. Here's it all subbed in. Take my word for it. I did check the maths and it does in fact equal 0. So there we go, success. 1 plus I is indeed a root. Now, let's chuck it into the derivative. So here is p dash x, our first derivative of the polynomial. Yeah, not going to go over how to differentiate. You probably already know how to do that. All right, let's chuck in 1 plus I. So here's 1 plus I subbed into the derivative, and would you believe it? Once again, we get an answer of 0 that I can't really fit the working out on. That's a real shame. Anyway, this is sufficient proof for us to say, all right, we have a root of the polynomial, and we also have a stationary point or a turning point. Therefore, we have shown pretty conclusively that 1 plus I is indeed a double root of the polynomial. Sweet as. All right. Part B, find the other 4 roots of the polynomial and hence express it as a product of real, linear, and quadratic factors. Okay, cool. So a degree 5 polynomial in the complex field will have 5 roots. We've got 1 of them. Well, we actually can't have 2 of them because we just figured out the 1 plus I is a double root. All right. Now, what's cool about this is that if 1 plus I is a double root, it means that the conjugate, 1 minus I, is also a double root. So even though there are 5 roots, we actually already know 4 of them. Okay, we have 1 plus I is doubling up. The conjugate is doubling up. There's only 1 left over. Let's just call it alpha. We can pretty quickly solve for this by summing the roots and setting it equal to negative b over a, which in this case will be 5. All these conjugates cancel out. Sorry, all these imaginary terms cancel out. And we end up with 4 plus alpha is equal to 5. So very quickly, we've figured out that the last root is indeed 1. So we've got 1, 2, 3, 4, 5 roots all found. Now, writing our polynomial all nice and factorized looks like this. Okay, now the tricky part, we've got to make this have real quadratic factors. So these 4 actually, complex factors need to be smooshed together and realized. So let's do that. If we expand out our interior brackets, which I'm getting sick of saying, let's think of a clever way of multiplying these together. Keep in mind we've got the same thing doubling up, so we can take some shortcuts. Okay, x minus 1 minus I and x minus 1 plus I. We can expand these two as a cheeky little difference of 2 squares. And then because we've got the same thing here, we can just do that and square it. Okay, so difference of 2 squares with these 2 bracketed terms. And I'm just going to square the whole thing because, like I said, it's doubling up. Okay, inside here we get x squared minus 2x plus 1, and then we get minus I squared also turns into 1. So this term here works out to be x squared minus 2x plus 2. We're just going to put a square there because we've got the extra brackets, and then an x minus 1 just chilling on the end. And there we have our factorized quintic polynomial using only real and quadratic factors. All right, awesome. Did I do example 6? Oh, of course I did. All right. Cubic polynomial, m and n are integers. That's cool. All right, show that the polynomial evaluated at negative I is equal to 1 plus n plus I times 1 minus m. All right, let's chuck in minus I and just hope for the best and see what happens. Okay, polynomial evaluated at minus I. So we have minus I cubed. We have minus I squared, minus im, and then plus n. Okay, cool. Now, negative, when we cube it, is going to stay negative. So we have negative I cubed. Negative, when we square it, will go positive. So we have minus positive I squared. All right, just trying to be very careful here that I don't put a negative in the wrong spot and just completely screw it up. Okay, I cubed, as we saw earlier, is equal to negative I. So this front term actually works out to be I. I squared is minus 1, so minus 1 is plus 1. And now we're going to group together the imaginary terms, because we can see for our target, we have the imaginary term factored out. So grouping the two imaginary terms together, we have 1 minus m. Grouping the two real terms together, we have 1 plus n. And there was the target. So as long as you're very careful with your negatives and very careful with your I squareds and I cubes, it's not super hard to get the target, hopefully. All right, now for part B. When p of x is divided by x squared plus 1, the remainder is 6x minus 3. Find the values of m and n. Okay, whenever I see a question talking about divisors and remainders, my first thought goes to the form of a polynomial that we look at in extension 1, which looks like this. Okay? Yeah, if you've seen this before, hopefully this will make some sense, but we have a polynomial equal to dividing by something multiplied by the quotient, which is the result of the division, and then plus a remainder. Okay, so this is kind of like 11 equals 5 times 2 plus 1, to make it real simple. Okay, so when our polynomial is divided, so our divisor is x squared plus 1, the quotient we don't know, the quotient didn't say anything, so we'll just hope that doesn't matter. And our remainder is 6x minus 3. Okay, here's our polynomial. Now we want to try and figure out the values of m and n. Now m and n are in part A, which was achieved by subbing in the polynomial with negative I. So a bright idea for this one is let's take our form down here for p of x and let's substitute in negative I. The reason this is a really clever move is because x squared plus 1, if x is negative I, well, I squared is minus 1, so this in fact turns into negative 1. Negative 1 plus 1 is indeed 0, so this q of x term is being multiplied by 0, so it conveniently vanishes, which is why we don't need to even really know what q of x is. Okay? So we get minus 1 plus 1, so we get 0. This whole thing vanishes, and we end up with just minus 6i plus 3. Now this is cool because this is an expression of the polynomial evaluated at minus I. So we can compare this to our expression from part A and say, well, these two things need to be equivalent. That means we can solve for n and m. So we set minus 6 plus 3 equal to 1 plus n plus I times 1 minus m from part A. If we're comparing these two complex numbers and they're equivalent, it means that the real parts are equivalent. So 3 is equal to 1 plus n. And it means that minus 6 is equal to 1 minus m. Okay, so we can solve for n and say that n is equal to 2. We can solve for m and say m is equal to 7. And there we have our values of m and n. So yeah, really cleverly designed question where you get a quotient that doesn't really matter because everything just nicely cancels out and maths is beautiful. All right, I'm pretty tired. Is that the end? Oh, beautiful. HSC question from 2021, band 4 multiple choice. Which of these polynomials could have 2 plus I as a 0, given that k is a real number? I remember this one. This is, in my opinion, a pretty spicy multiple choice question. Took me a bit of scratching the head, but if you like a challenge, pause the video and see if you can figure it out. Otherwise, I'll go through a few hints in a couple minutes to help you get towards an answer. All right, here's some hints. So first of all, if 2 plus I is a 0, all these polynomials have real coefficients, so we can of course use the conjugate root theorem. All right, if we sum our roots together, we end up with 4 plus the unknown root of alpha is equal to negative b. Okay, I can't write in what b is because we don't know if it's 4 or 5, depending on which one we're looking at. Okay. All right, there's our sum of roots. Let's look at the sum of roots in product pairs. So 2 plus I times 2 minus I. Alpha times 2 plus I and alpha times 2 minus I. This is equal to C over A. Now in every polynomial, C is equal to K and A is equal to 1. So we can write C over A as just K. All right. Expanding out the left-hand side and tidying everything up, you end up with 5 plus 4 alpha is equal to K. All right, and our last equation is the product of the three roots, so alpha, beta, gamma. This is equal to negative d over a, but we don't know whether d is 0 or 5. So we get 5 alpha equals minus d. Now, your challenge is to answer this question. You've got to try and see which of these four polynomials, could have a solution that works with all three of these equations. Okay, so work through process of elimination, try and see which one can work for all three of these. You should only get one that works, and I can't remember whether I've circled it or not. Let's see. I didn't. Okay, so you got to figure it out for yourself. If you're super curious, you can of course look up the solution or the answer online, but I don't want to spoil it for you. So also, I don't know if I remember or not. Anyway, here are some recommended exercises for those who want some more practice out of Cambridge if you're using this textbook. All right, it's pretty late at night. Sorry about that. Thank you for those who watched. I hope this helped you in some way, and I'll catch you in the next, hopefully more lucid video. All right, ciao.